Blue light? Awesome. Okay, so this is 8.6 exponential growth and decay. And you can see the curve here. This blue curve is the exponential, right, that we just dealt with. And what we want to do this lesson is really try to get into some real life type scenarios or concepts is what the idea is behind lesson 8.6. So we're trying to get some real life situations and such. So growth. This is the curve of a growth. How do you know it's a growth? And I mentioned some of this on Tuesday. But as x, the input increases, and make no mistake, the x increasing is a left to right, right? You don't need to put this in, but what's the x value right there? 0. What's the x value right there? 2, 4, 6, 8. See, as my x value is increasing, what's happening to the y value? So watch. Right here, at 2, the y value looks to be like 1.2. At 4, the y value is a little higher, maybe 1.6. At 6, now the y value is up to 2 point something. At 8, the y value is up to 1, 2, 3, 4. You see how the y is increasing as the x is increasing? Well, that's the idea of a growth. So a growth is as the x input increases, the y, the output increases. As the input increases, the output increases. And by the way, for most of our situations in this scenario with exponential growth and decay, usually this x scale is time. Most of the time, it's time. And the vertical scale is usually an amount. If you're talking money, that might be in dollars or kroner or pesos or euros or rubles or whatever, if you're talking money, right? So that's the situation. So what kind of things can have a growth? Population. Population. And when they take data of population over a good amount of data points, they're able to figure out whether population is a growth or a decay. Unfortunately, in our civilized, which is really uncivilized world today, there's aspects where abortion is popular, and abortion has a great effect on the population. Instead of population being a growth, what can happen in effect is population can be a decay instead. It can go either way. You can have population growth or population decay. In some countries, they limit how many children you can have. I know one country in particular, they limited that you're only supposed to have one child per family. Well, if 2 people have one child, what's going to happen to your population? It's going to go down. I mean, every 2 people are having one child. Obviously, you're not going to have a population growth. So population, bacteria. Bacteria. Has any of you guys ever done a mold or bacteria science project? You know, you start looking in the beginning, you don't see a whole lot, and all of a sudden, man, you know, you got it all over the place. And it's an exponential growth curve. By the way, when you get sick with something that would require an antibiotic, you have to be careful to keep taking the antibiotic until it's completely gone. And the reason is whatever is causing you to be sick is on an exponential growth in your body. And when you start taking the antibiotic, it starts knocking it down. But if you don't knock it completely out and it's still there, like let's suppose, don't need to put this in your notes. You're right here and you're finally sick. There's enough of the virus to get you sick, okay? And you're finally sick. You start taking antibiotics and you knock it down to here and you feel good, so you stop taking the antibiotic and you don't take it all. you still have this amount of bacteria in you, and what's going to happen is it's going to start going again from there and right back up. And so that's the situation. Bacteria is a real life situation. Viruses, such like that. Investments. At least you hope your investments are growths and not decays. And all of these can really go both ways. You have population growth or population decay. Bacteria can grow or decay. Investment can grow or decay. You would hope that your monetary investments would grow. All right, so decay, you can see, is the opposite. Again, we're still looking at an increase in the input, the X value. And again, we got time here, and we got the amount here. So let's suppose this represented an investment. Let's use an investment example. This would be a very bad investment. Let's suppose this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we'll call this $10,000. So at time 0, you have a $10,000 investment. What would that mean? Can anybody explain what that means? Time 0, you have $10,000 investment. Matt? Exactly. When you first started, you started with $10,000. Maybe you bought $10,000 of U.S. savings bonds. Maybe you bought $10,000 of Apple stock. Maybe you bought $10,000 of bonds. Maybe you bought $10,000 of physical gold. Right? Your investment, $10,000. Unfortunately, over time, when we get down to here, and I don't know, we'll do this in months. It is a really bad investment. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that just so happened to be 10. 10 months, what do you got left? A little over $1,000 left. So that was not a very good investment. Our money is decaying. We don't like that. Okay, you don't want your money to decay. But notice, as the X increased, as time increased, right? What happened to the output value, the Y? It decreased. And those are decays. Again, you can have population in decline. Population can be in decline. By the way, it's not good for a nation to have population in decline. It's not. And I mentioned the word abortion earlier, and I will throw out that there's more to the abortion issue than meets the eye. And evil men decide evil things, and things happen as a result. But anyhow, population, bacteria. Bacteria can go up or down. Investments can go up and down. This last one, though, is only a decay, and that's radioactivity. I wish I had time to show you the decay curve of radioactive carbon-14. Anybody ever hear of the use of carbon-14 in a practical manner? How carbon-14 is used practically? John? For dating purposes, exactly. Carbon-14 is used for dating purposes. And again, I don't want to, I haven't looked at the curve in a while. Don't put this in your notes, but if I remember right, I know it's a decay. You get down to this flat part of the curve. Are we getting very much change in the output when you get to the flat part? You can go lots of time with little change. If I'm remembering right, like 5,700 years is like right around there. And so once you get to that flat part of the curve, little itty bitty bits of calculation give you a lot of big changes. And I mean, you can be way down here and it hadn't changed a whole lot. You could be down there at 3.2 billion years and your output is very little different, which means it's really hard to be accurate past about 6,000 years, most would say. But anyhow, that's a whole nother story. All right, so decay. Look, does it make sense? Look at the two curves. Doesn't the first one look like a growth? Doesn't that look like a decay? All right. The one's growing, it's heading up, and the other one is heading down. And it's a whole lot better to be heading up than to be heading down. All right, so some patterns. So I wrote them out for you, but we need to do some defining here. So here's some formulas, patterns. The A is the initial amount. The initial amount. If you were infected with a disease, the initial amount can't be 0. You would never get the disease, but if it's greater than 0, you're going to be infected. This A is exactly the same. It's just these are two formats of the same concept. And I want to show you both formats. They use a capital A in the left one and they use a lowercase a in the right one. I color coded them so you would know. So that's the initial amount. What in the world would the T be? What would you guess? Time. T is the time. Now in the other format we usually use an X, but again, it's almost always the time. All right, and then we got the base, and I put the bases in red. Right, the formula on the left, doesn't the T exponent go to everything in the parentheses? So isn't everything in the parentheses the base of the T? Right, we learned bases and exponents. And on the right, the B is the base. Remember, the exponent on the right only goes to its base. It only goes to the B. You don't need to draw that in. I'm just trying to get you guys to focus and remember and understand. Right? That X only goes to that B. Okay, so what about these bases? What are they? Well, before I get down there, let me just say what R is. R is considered the growth rate. R is the growth rate, which could be a growth or a decay. It depends on its values, and that's what we're going to learn to figure out here in a minute. Okay? The growth rate. Notice the second form does not have an R in it, but we can write it and make an R. We'll do that in just a little bit. All right, let me raise this up. Okay, so we need to see the patterns. So the base is called the growth factor. The whole base is called the growth factor. So the one on the left, the base is the 1 plus the R. The 1 plus the growth rate is called the growth factor. And the one on the right, the base is the B, so the B is the growth factor. So the base on the left is 1 plus R, that's the growth factor. The base on the right is B, and it's called the growth factor. Well, it's pretty simplistic. If when you add 1 to R, you're less than 1, look at the original formula. Don't do this in your notes. You're taking an initial amount and you're going to multiply it times something. Well, if the base is less than 1, you're going to multiply this times something lower than 1. And what's going to happen to the initial amount? It's going to go up or down? It's going to go down. It's exactly what's going to happen. Or if the B is less than 1, again, you're going to multiply that initial amount times something less than 1, and you're going to have a decay. You're going to have a decay. However, if 1 plus R is greater than 1, or the B is greater than 1, when you multiply the initial amount by it, you're going to have a growth. That should be green. You're going to have a growth. Come on, green. You're going to have a growth. Now, I'd love to show you an example right now. If I have time, I'll come back and we'll do an example of an investment. And I'll show you how that can work out. All right, so here I have everything again. Let me get my shade up here so I can focus you guys. So look, we just did this a minute ago. I have it because I want you to be able to see it on this page. So that's why it's the exact same thing we just did a minute ago. And so it's all right there again, because this is how we need to figure out what's going on. All right? So we just did this a second ago, so let's begin to apply it. So number 3 says, hey, give the initial amount, the value of the growth factor, and if it's a decay or growth. So they want to know 3 things. They want to know the initial amount, they want to know the growth factor, and they want to know if it's a decay or a growth. And honestly, as long as you remember what each thing is, it's pretty easy if you remember the patterns. Okay, so number 1, first question, what's the initial amount? On 3, if you know it, say it. 1, 2, 3. It's 2,000. It's the A value. It's 2,000. We don't really know 2,000 what? We don't know $2,000, 2,000 euros, 2,000 water molecules. We don't know what it is. Okay. So next question, what's the growth factor? I'll give you a minute to think. On 3, I want you to tell me the growth factor. Here we go. 1, 2, 3. So I heard 2.5, 3.5. I heard 2 answers. How many are 2.5? How many are 3.5? And does anybody have anything else? Because that's definitely not everybody. Kyle? Okay, so parentheses 1 plus 2.5, close parentheses to the t. How many agree with that? All right, so we got a few there. All right. The growth factor is the base, which is the 1 plus r in the left pattern and the b in the right pattern. Which one does this fit, the left pattern or the right pattern? Left pattern. What's 1 plus 2.5? And it's simply 3.5. Don't overthink it. It's the 3.5. So last question, is this a decay or a growth? Say it if you know it. It's a growth because 3.5 is bigger than 1. You're looking at that 3.5. It's bigger than 1. That initial amount's increasing. At time 1, you're going to have 3.5 times 2,000. So where are you up around 7,500, something like that, whatever. Okay, let's do another one. Now, I'm trying to give you a couple of different formats. Again, you guys, you've got right at the top of your paper the patterns there to look at, right? Oh, no, no color. We're surely not going to know what in the world to do on this one. Somebody raise your hand, tell me the initial amount. Quinn? 32 grand. I agree. 32,000. 32,000. Somebody raise your hand, tell us the growth factor. What is the growth factor? Eva? All right, don't write anything yet. How many agree with Eva? 0.25. All right, you'd be all the correct ones. So again, you're just doing 1 minus 7, right? 0.07, I'm sorry. 1 minus 0.75, and that's going to be 0.25, right? Okay, so last question. Somebody raise your hand and tell us, is this a growth or a decay? Curly, was that your hand? Decay. Don't write anything yet. How many agree with Curly? It's a decay. It is a decay because 2.5 is less than 1. And you're going to end up multiplying that initial amount by something smaller than 1. You might say, but you're not even talking about the exponent, Mr. Scarfy, but the exponent is just going to make that number smaller. Take your calculator. I want you to punch in 2.5 on your calculator. 0.25, right? That's the base now, isn't it? 1 minus 0.75 is 0.25. Now, do you remember your Y to the X button or your X to the Y button or your caret button? Hit that next. You got one of those buttons for exponents. Then punch in a 5 for an exponent. So we'll see what happens when t is 5. Look what happened to the number. Did it get bigger or even smaller? Even smaller, exactly. That's what happens when you do an exponent to something less than 1. It gets even smaller the bigger the exponent is. So again, this is going to continue to get smaller. It's a decay. It is a decay. Again, please ask questions as we go. so I can explain things for you and help you out. John? Well, there's no such thing as negative time unless you want to go back in the past or you're a time traveler or you know something that we don't know. Okay? All right. So, next example. All right. Again, you're trying to size up the pattern. Who can give me the initial amount? Who wants to give me the initial amount? Gabe? 750 is the initial amount. Growth factor. Growth factor. Kyle? Don't write it yet. How many agree with Kyle? 1.5. It is, right? It's the B. It's the second one. Growth or decay? Growth or decay? Come on, participate. Participate. Dave? How many agree with Dave? It's a growth. And it's all the correct ones, right? So we're bigger than 1. All right, see how this goes? Again, if we learn the patterns, then we're okay. And it's not hard. Okay. Initial amount. Somebody give me the initial amount. Looking for somebody new. Wesley? 5 is the initial amount. Looking for the growth factor. Tommy? 7 is the growth factor. Decay or growth? Josh? It is a growth. Okay. Let's keep going along this line so I can cover all the possible bases, right? Just trying to give you guys examples of all the different ways these can turn out. So again, notice the top is exactly what we've done before. It's there so you can look at it, right? Because that is what's going to help you to know what to do, correct? All right, so we got a few more examples here. Let me do my shade so I can focus your thoughts. Am I still recording, I hope? Yeah. Okay. So here we are, and we've got another problem. And this time, though, we're asking for the growth rate. So be careful. And then we want the growth rate as a percent. So a little different problem. All right. Anybody want to go for the growth rates? Growth rate. Again, I'm looking for a new hand. Jeff? Don't write it yet. How many agree with Jeff? 2.5. Let's see if I can help you out a little. We're looking for the growth rate right now, right? Okay. See anything on there that mentions growth rate? Do you see this right here? Okay. Hopefully you put that on yours too, right? I hope. Hope you did. Okay, so let's go back to the present. So how many now agree with 2.5? This should be all of you. The R is the growth rate. Now, this second part should be pretty easy. What is 2.5 in percent form? Somebody raise your hand, tell me 2.5 in percent form. Come on, every hand should be up. 2.5 in percent form. I'm going to have to start calling on you guys that aren't volunteering. So you want to volunteer if you know. Looking at everybody's hand up, I've already called on. Gavin, have I called on you yet? Okay, go ahead, Gavin. 0.25%. Anybody agree? Uh-oh, a couple agrees. Somebody else give me something. Seth, were you going to put your hand up? I saw your hand begin to go up. What were you going to say? Just go for it. Can only be right if you try, but, you know, people are wrong anyhow. How many agree with Seth? 250%. Is the majority always right? No, but they are in this case, right? Yeah, 2.5 is 250%. Hey, you guys remember percents. 0.3 is 30%, right? 0.05 is 5%. 1 is 100%. 2.5 is 250%. Gee, if that was your money, you would love a 250% growth rate. You would be happy. Although Money isn't the only thing that will make you happy, and sometimes it'll make you sad. Okay, let's do another example. Growth rate. Growth rate. Need somebody with some turn. Go for it, Dave. 5.2. How many agree with Dave? 5.2. Majority. Anybody have anything else? Tom? Tommy says 4.2. Anybody agree with Tommy? You're standing alone, Tom. Tommy, what in the world? You're all by yourself. What did you do to think that it's... What did you do to figure out that it's 1 point or 4.2? Because Tommy said, let me put it in the proper form here so I can read the R value. That's what Tommy was thinking. And I agree with Tommy. It's 4.2, people. There's another glaring example of the majority is not always right. Hey, you got to read the R. It wasn't in the right form. You got to put it in the right form. Got to get the R. All right, we're off in the pirate land. Does that make sense now, though, when I explain it, right? You need the R. And so now, what is the percent growth? Say it if you know it. 420%. Remember, to change a decimal to a percent, move the decimal point 2 places to the right, add the percent symbol, right? 2 places right, add the percent symbol. All right, trying to show you different possibilities. A few more. All right, growth rate. Growth rate. Growth rate. John? Yeah, and in actuality, negative 0.7. It's actually negative. We don't bother saying it when it's positive, but we say it when it's negative. 0.7. What is negative 0.7 for a growth rate? Gabe? Correct. Negative 70%. Do we have a growth or a decay here? Do we have a growth or a decay? We have a decay. Yep. We're down 70% in time. All right. Here's another one. Growth rate, Matt? 0.3. You know, these could be any kinds of, remember functional notation, Matt? This is usually goes along with the independent variable, and notice we have a D there. Notice here again we have a D. So it depends upon the application. I'm trying to show you as many different looks so the look doesn't throw you guys off. But again, the independent variable is always the exponent. And so f of D, f of Q could be anything really. Okay. All right, so our growth rate is 0.3. So what is our growth rate is 0.3. What is that in percent form? 0.3, 30%. So again, once you see what's going on, then that's not too difficult. Okay, we're going to finish off with a couple of other examples. Write the function in the form of, and they tell us the form right here, right? F of t equals a b to the t. Or is that? Yeah, it's to the t. And state if it's a growth or a decay. Okay. The initial amount is 37, and the growth rate is 4/3. F of t equals, what's the value of a? Say it if you know it. 37. What do I do with this 4/3? Because it's the growth rate. Zach? I could, but I'm telling. What do I do with the formula, being it's a growth rate? Kyle? You have to, right? It's a growth rate, therefore it's 1 plus this 4/3. Right? The 4/3 is the growth rate, and the exponent they gave us is t. Now, are we in the complete form they asked for? Not yet. We have to add up b. Guys, I hope we can add up 1 and 4/3 in our head? Common denominator. How many thirds is 1? How many thirds is 1? 3/3. What's 3/3 plus 4/3? 7/3. You guys can do that in your head. So that would be the correct form for that, right? F of t equals 37. Excuse me. Times 7/3 to the t. Okay, last one. Again, we got to do the proper format. So we got f of t. Initial amount, that's the A, right? 2,100. Okay. I got a growth rate of negative 20%. So what goes in my parentheses right now in the beginning? Zach? Great. Right? Agree? That's a negative 20% minus 0.2. And so our f of t is going to be 2,100 times 0.8 to the t. Oh, we didn't say growth or decay. So is A, let's go back to A, growth or decay for A? Growth, right? 7/3 is bigger than 1. For B, growth or decay? Decay, because we're less. All right, let me go back real quick. You guys already have the page number at the bottom of your page to do. If you have your notes with you, it should be easy, but everybody just stop for a second. Let me just go back one second here. I just want to show you what would happen to an investment. Let's suppose you had a rich uncle and he put $2,000 in an account for you and he was able to get 8%, 8.5% interest. Just watch. 8.5% is 0.085. Okay? And he put that in, let's suppose at age 18. So T is 18, right? 18 years. You would have in your account 8,000, you don't need to write this, $8,689.91 at age 18. Let's suppose you decided to leave it in there till you're 40. Now the exponent's 40, all right? That just one time $2,000 investment at 8.5% would now be $52,266 and some change. Just the initial $2,000. Let's suppose you waited until you were 65. Remember the curve, right? Goes like this. If you can get away from this area and start getting over into this area, it starts getting nice. At age 65, you would have $401,757. And by the way, if that would have been 10 grand, you'd have $1 million. If that would have been 10,000 one-time investment, no more put in it at all, 8.5%. You'd have $1 million at age 65. You could get it. The thing is, percents change. The more money you invest, the better percent you get too. That's why the rich get richer. The rich get richer because they invest their money. They start doing all this stuff. You know, your rich kid, what do they put, 100 grand down for their kids, you know, at age? So now the initial amount's 100,000, not 2,000. All right, make sure you do your homework. Bottom of the page, due tomorrow.